Hi to everyone, myself Dr. Dhananjay Rao, working as assistant professor in the Department of Chemistry. Today I am going to teach about biodegradable polymer. In this session I am going to cover these topics. What is biodegradable polymer, definition, purpose of the biodegradable polymers, and advantages of biodegradable polymers. What are the advantages we have with biodegradable polymers, and polylactic acid synthesis, properties and applications, and also polyvinyl acetate synthesis, properties and application. In this session I am going to cover what is biodegradable polymers and definition and purpose of the biodegradable polymers, and the examples for biodegradable polymers are polylactic acid and polyvinyl acetate. And in this session I'm going to cover the synthesis and properties applications of polylactic acid and polyvinyl acetate. I'm going to teach about these topics. First we are going to learn about the what is biodegradable polymer and definition of the biodegradable polymer, and what is the purpose of biodegradable polymers. I'm going to teach. See, the biodegradable polymers. Generally, polymers do not undergo biodegradation even after long time. Even after long time, the polymers will not undergo any biodegradation. It will take long time to degradation. The polymers generally takes long time to biodegradation. It is very difficult to manage the polymers waste in the environment. So the biodegradation takes a lot of time for the polymer. So it is difficult to manage the polymer waste in the environment. It is very difficult to waste polymer waste in the environment. It is very difficult to manage the polymer waste in the environment because of the polymers generally takes long time in the environment. Okay. To avoid this, biodegradable polymers usage to manage the wastage in the environment and the degradation, the polymers takes long time to degradation. So to avoid this, the biodegradable polymers we can use instead of synthesized polymers. We can synthesize biodegradable polymers. It will undergo biodegradation in less time. So to avoid this, the biodegradable polymers we can use it. They degrade quickly, do not cause such environment problems. These biodegradable polymers quickly and do not cause any such environmental problems. Biodegradable polymers quickly undergo degradation and it do not cause such environmental problems. To biodegradation, these biodegradable polymers takes less time and it will not cause any such environmental problems. See, definition of biodegradable polymers. The biodegradable polymers are polymers which undergo degradation by the naturally occurring microorganisms like algae, fungi and bacteria. What is biodegradation polymers? The biodegradable polymers are polymers which undergo degradation by the naturally occurring microorganisms. What are the microorganisms? See, like algae, fungi, bacteria. In presence of these microorganisms, these biodegradable polymers will undergo biodegradation very fastly and rapidly. That is called biodegradable polymers. See, what is biodegradable polymers? The biodegradable polymers are the polymers which undergo degradation by the naturally occurring microorganisms. Naturally occurring microorganisms like algae, fungi, bacteria. In presence of these microorganisms, the biodegradable polymers undergo degradation very fastly. The biodegradable polymers are classified into two types. The biodegradable polymers are classified into two types. See, what are they? Naturally biodegradable polymers. First one is natural biodegradable polymers and the second one is synthetic biodegradable polymers. The biodegradable polymers are classified into two types. First one is natural biodegradable polymers and second one is synthetic biodegradable polymers. See, natural biodegradable polymers. These polymers undergo biodegradation by enzyme catalyzed reaction in aqueous media. What are the natural biodegradable polymers? The type of polymers which undergo biodegradation in presence of enzyme catalyzed reactions in aqueous media. In presence of enzyme catalyzed reactions in aqueous media, those polymers are called naturally biodegradable polymers. Thus, biodegradable polymers are called natural biodegradable polymers. What are the natural biodegradable polymers? These polymers, the natural biodegradable polymers, will undergo biodegradation by enzyme catalyzed reactions in aqueous media. Is called naturally biodegradable polymers. The second one is the synthetic biodegradable polymers. Synthetic biodegradable polymers, and also called man-made biodegradable polymers. We can call also man-made biodegradable polymers are synthetic biodegradable polymers. These polymers also undergo biodegradation by enzyme catalyzed reactions in aqueous media. Synthetic biodegradable polymers will also undergo biodegradation in presence of enzyme catalyzed reactions in aqueous media. What is natural biodegradable polymers? These are available in nature. Okay, these are the natural biodegradable polymers are available in nature. These polymers undergo biodegradation by enzyme catalyzed reactions in aqueous media. What are the synthetic biodegradable polymers? We can also call man-made biodegradable polymers. Man-made biodegradable polymers are synthetic biodegradable polymers. These also will undergo degradation by enzyme catalyzed reactions in aqueous media. See, advantages of biodegradable polymers. What are the advantages or what are the need of the biodegradable polymers? See, it is cheaper than normal polymers. Compare the prices of the biodegradable polymer and synthetic polymers. The biodegradable polymers are the very cheaper than the synthetic polymers. The emission of CO2 is reduced. In the case of the synthesis of biodegradable polymer, the emission of CO2 is reduced. Okay, the emission of CO2 is reduced. It takes less time to break down. Okay, to compare the general polymers or synthetic polymers, the biodegradable polymer takes less time to degradation or break down the bonds in the polymer biodegradable polymers. It takes less time to break down. The biodegradable polymers takes less time to break down. These polymers are renewable. The biodegradable polymers are renewable. These polymers are renewable. The biodegradable polymers are renewable. It is good to the environment, but the biodegradable polymers are good to the environment. The biodegradable polymers are good to the environment. These are non-toxic. Biodegradable polymers are non-toxic, easy to recycle. The biodegradable polymers are easy to recycle and requires less energy to produce. It takes less energy to synthesis. It takes less energy to synthesis. See, what are the advantages of the biodegradable polymers? It's cheaper than the normal polymers. The biodegradable polymers are cheaper than the normal polymers, and the emission of CO2 is reduced. The emission of CO2 is reduced. Okay, it takes less time to break down. The biodegradable polymers takes less time to break down. These polymers are renewable. The biodegradable polymers are renewable, and it is good to the environment. The biodegradable polymers are good to the environment. These are non-toxic. The biodegradable polymers are non-toxic and easy to recycle. These are easy to recycle and requires less energy to produce. Requires less energy to synthesis or produce. These are the applications of biodegradable polymers. See, the first example of biodegradable polymer is polylactic acid. What is polylactic acid? See, it is derived from renewable sources such as starch and sugarcane, etc. We can prepare polylactic acid by using this starch and sugarcane. Okay, these how we can prepare polylactic acid can be prepared by using this starch or sugar cane. Okay, how we can prepare? See, preparation. It is prepared by the catalytic dimerization of lactic acid, resulting in the formation of lactate monomer. It is prepared by the catalytic dimerization of the lactic acid, resulting in the formation of lactate monomer. First, we can collect lactic acid from the starch and sugarcane. We can prepare lactic acid from the starch or sugarcane. Okay, by using malt enzyme. By using malt enzyme, we can prepare starch we can prepare polylactic acid from starch and sugarcane, etc. Okay, the obtained polylactic acid is undergo catalytic dimerization. Forms lactate monomer. It forms lactate monomer. See, this is the structure of lactic acid. See, what is the structure of lactic acid? CHOH, CH3, COH and C double bond O. This is the carboxylic acid function group and OH function group. It will undergo dimerization, catalytic dimerization. In presence of catalyst, it will undergo dimerization and remove water from the dimerization. Dimerization, but nothing but two lactic acids react together, and in this condensation, water is eliminated. In the presence of catalytic dimerization, it takes place. Elimination of water takes place. Okay, it forms cyclic lactate monomer. Two lactic acid molecules reacted together, and the water molecule is eliminated. It forms the cyclic lactate monomer. This is the cyclic lactate monomer. Okay. In presence of stannous octanoate to give polylactic acid. In presence of stannous octanoate to give polylactic acid. This cyclic lactate monomer will undergo polymerization. It forms polylactic acid in presence of stannous octanoate. Stannous stannous octanoate means CH3 CH2 6 C double bond O minus. Okay. Similarly, it will bonds with 2 SN octanoate 2. This is the octanoate structure. What is the octanoate structure? CH3 CH2 6 C double bond O minus 1 7 8. 8 carbons are there, so we can call octanoate. The C double bond O minus is there, so we can call it is octanoate. So this stannous reacts with this one and O minus C double bond O CH2 6 and CH3. This is the structure of stannous octanoate. In presence of this catalyst, okay, the cyclic lactate monomer will form polylactic acid. This is the structure of polylactic acid. How we can prepare polylactic acid? We can collect lactic acid from the starch or sugar cane. Okay, then the polylactic acid will undergo dimerization in presence of catalyst. Catalytic dimerization takes place. It forms the cyclic lactate monomer. Two lactic acid molecules react together, undergo dimerization, forms cyclic lactate monomer. This cyclic lactate monomer in presence of the stannous octanoate. The stannous octanoate is a catalyst. In the presence of this stannous octanoate catalyst, the cyclic lactate monomer will undergo dimerization. It will form polylactic acid. Okay, this form polylactic acid. In first step, lactic acid will convert into cyclic lactate monomer. This is the lactate, the C double bond O. Okay, this cyclic is there, so cyclic lactate monomer. The C double bond O function group is present in the cycle, that is called lactide. Okay, this is a cyclic lactate monomer. The lactic acid in presence of the lactic acid, two molecules of lactic acid reacts together and forms cyclic lactate monomer. Okay, in presence of the catalyst. Okay, in presence of the stannous catalyst, this cyclic lactate monomer will undergo polymerization, forms polylactic acid. In this case, the catalyst is stannous octanoate. Okay. See, we can represent other way also. This is the lactic acid structure. Okay, and it will undergo dimerization. Okay, it will undergo dimerization. It will form lactate. This lactate will in presence of stannous octanoate. Stannous octanoate. In presence of stannous octanoate, the lactate will undergo polymerization. It will form polylactic acid. This is the monomer structure present in the polylactic acid. Okay, the first step, the lactic acid convert into the lactate. Okay, lactate. The lactate in presence of stannous octanoate, it will form polylactic acid. This is the synthesis of the polylactic acid biodegradable polymer. See, properties of the biodegradable polymers. Polylactic acid is a linear and thermosetting plastic polymer. The polylactic acid is a linear and thermosetting plastic. It is example for the thermosetting plastic, and it will undergo addition reaction, and it is a linear one. The polylactic acid is a linear and thermosetting plastic. It has around 37% crystalline nature. Okay, the polylactic acid, this polymer contain 37% crystalline nature, and the remaining percent will be in amorphous state. Okay, the polylactic acid has a 37% is in crystalline nature and remaining percent is in amorphous state. The biodegradation of D isomer is slower than the L isomer. If compare the polylactic acid, it contains D isomer and L isomer. The D isomer is slower. Biodegradation takes place. The D isomer will take biodegradation takes slower than the L isomer. Means the L isomer takes very less time compared with the D isomer to take biodegradation. Okay, to participate in biodegradation, the L isomer will take less time and the D isomer takes more time. Okay, it is soluble in benzene and THF. The polylactic acid is soluble in benzene solvent and also THF. THF nothing but tetrahydrofuran. It is soluble in benzene and tetrahydrofuran. The polylactic acid is soluble in the tetrahydrofuran and benzene. See, what are the properties? The polylactic acid is a linear and thermosetting plastic. It is example for the thermosetting plastic. It has around 37% crystalline nature. That it has 37% crystalline nature and remaining percent will be in amorphous state. The biodegradation of D isomer is slower. The biodegradation of D isomer is slower and L isomer is faster. The polylactic acid is in two forms. One is D isomer form and other one is L isomer form. The L isomer form undergo biodegradation very rapidly compared with the D isomer. D isomer takes a long time. It is slower to take biodegradation. It is polylactic acid soluble in benzene and THF. The polylactic acid soluble in benzene solvent as well as tetrahydrofuran solvent. See, applications of this polylactic acid. The polylactic acid used for making medical implants like screws, pins, anchors, etc. Polylactic acid used for making medical implants like screws, pins, anchors, etc. By using this polylactic acid, we can prepare screws, pins, anchors in medical implants. It is used in a number of biochemical applications like drug delivery devices and dialysis media. Okay, but drug delivery applications and also for dialysis media, we can use the polylactic acid. It is used in a number of biochemical applications. Okay, you can use it for biochemical applications like drug delivery and also dialysis media. It is used in the preparation of bioplastics for packing food, disposable tableware. By using this biodegradable polymer polylactic acid, we can prepare plastics for packing foods and disposal tableware. Okay, we can prepare these things by using polylactic acid. It is also used for making compostable packing materials, food packing, etc. By using polylactic acid, we can prepare compostable packing materials and also food packing materials by using this polylactic acid. These are the applications with the polylactic acid. The next example is the polyvinyl acetate. The polyvinyl acetate is the other example for the biodegradable polymer. See how we can prepare the polyvinyl acetate. The polyvinyl acetate is a vinyl polymer that is prepared by free radical vinyl polymerization. The monomer is vinyl acetate. Okay, the monomer is vinyl acetate. The monomer vinyl acetate will undergo free radical polymerization. Free radical vinyl polymerization. It will form polyvinyl acetate. The monomer is vinyl acetate. The vinyl acetate will undergo free radical vinyl polymerization. It will form polyvinyl acetate. See, this is it contains double bond. Okay, in presence of light or sunshine. Okay, sun. This double bond will undergo homolysis breakage. Means it will form this double bond form two free radicals CH2 CHO C double bond O CH3. One free radical here and one free radical here. This bond breakage takes place in presence of sunlight. Okay, it will form two free radicals. Okay, other molecules also same, like it will undergo homolysis. Okay, it will form two O C double bond O CH3. Okay, there is a bond formation takes place between these two free radicals. Like this, it will form one linear chain that is called polyvinyl acetate. In this polyvinyl acetate, the monomer is the vinyl acetate. It will undergo free radical vinyl polymerization. Okay, this will form the polyvinyl acetate. This is the polyvinyl acetate structure. See the properties of polyvinyl acetate. The polyvinyl acetate is a amorphous polymer having a glass transition temperature between 30 to 45 degree centigrade. The polyvinyl is a amorphous polymer. It contains amorphous in state. It will not contain crystalline nature. Okay, the polyvinyl acetate is a amorphous polymer having the glass transition temperature in between 30 to 45 degree centigrade. It contains the glass transition temperature between 30 to 45 degree centigrade. It is resistant to oil, grease and solvent. The polyvinyl acetate is a resistant to oil and grease as well as solvents. It has high tensile strength and flexibility. The polyvinyl acetate has high tensile strength and flexibility also high. Degree of polymerization of PVA is between 100 to 5000. The degree of polymerization in polyvinyl acetate is 100 to 5000. Okay, and it can be treated with alkali, which gradually result a polyvinyl alkyl and alkali acetate. See, the degree of polymerization of polyvinyl acetate is 100 to 5000, and it can be treated with alkali in presence of alkali, which gradually result in the polyvinyl alcohol and alkali acetate. See, the structure of polyvinyl acetate is CH2, okay, C double bond O, CH3, okay. In presence of alkali means in presence of base OH minus, okay, it will take what will form? It will with gradual results in the polyvinyl alcohol. It will form polyvinyl alcohol, okay. N. In presence of which it will form polyvinyl alcohol and alkali acetate, okay. In presence, it will undergo here it attack and O minus it will takes place, okay. It forms gradually polyvinyl alcohol, okay. So this OH minus attack here, it takes here, okay. It will form CH2, C double bond O, OH, N, okay. This is the structure of polylactic acid, and it will form CH3O minus Na plus. In place Na, if you take NaOH, it will form CH3O minus Na plus and CH2, C double bond O, OH, okay. It will form polylactic acid as well as the alkali acetate, okay. It will form polylactic acid and alkali acetate, okay. In presence of alkali, it will form polylactic acid and this alkali acetate. The polyvinyl degree of polymerization of polyvinyl acetate is 100 to 5000, and it can be treated with alkali. In presence of alkali, the polyvinyl acetate is gradually results a polyvinyl alcohol and the alkali acetate. It is decomposes rapidly above 200 degree centigrade. Above 200 degree centigrade, the polyvinyl acetate will undergo degradation or decomposition, okay. It undergoes pyrolysis at higher temperature. It undergoes pyrolysis at higher temperature. Polyvinyl acetate does not cross link and it can be dissolved in many solvents other than water, okay. The polyvinyl acetate will not form any cross linkages, so it dissolved in many solvents except water, okay. The applications of polyvinyl acetate. The emulsified polyvinyl acetate is used in water-based adhesives like paste and glues. The emulsified polyvinyl acetate. If you add any emulsifier to the polyvinyl acetate, we can use it for water-based adhesives. Okay, water-based adhesives like paste and glues. We can prepare by using polyvinyl acetate. We can prepare paste and glues. It is used in eye drops and hard contact lens solution as a lubricant. It is used for the eye drops and hard contact lens solutions like lubricants, okay. It is used as protective chemical resistant to glow. It is used as a protective chemical resistant to the glow. It is also used in 3D printing as support structure. It can also use it for 3D printing as a support structure. It is used as thickness modifier in a polyvinyl acetate glues. It is used in a thickness modifier in polyvinyl acetate glues. See, in this one what we have seen, what is the definition of biodegradable polymer and the examples for applications of biodegradable polymers, and in the what are the natural biodegradable polymers and synthetic biodegradable polymers, the applications of biodegradable polymers, and the examples for biodegradable polymers are polylactic acid and polyvinyl acetate. See, in the polylactic acid, the polylactic acid is obtained from the starch and sugarcane. Okay, this obtained polylactic acid will undergo catalytic dimerization. Okay, it will form cyclic lactide monomer in first step. In presence of stannous octanoate, this cyclic lactide monomer will undergo polymerization, will form polylactic acid. This is the structure of polylactic acid. The monomer in the polylactic acid, lactic acid, and it will undergo dimerization from cyclic lactide monomer. This is the monomer in the case of monomer in the case of polylactic acid. Okay, this is the monomer. This is the structure of polylactic acid. In this case, we have to use the stannous octanoate as a catalyst. Okay, these are the properties of the polylactic acid. What are the properties? See, the polylactic acid is a linear and thermosetting polymer, and it is around 37% content crystalline nature. The remaining percentage is in amorphous in nature. The biodegradation of D isomer is slower than L isomer. Okay, it is soluble in benzene and THF. The polylactic acid can soluble in benzene as well as tetrahydrofuran. The applications of polylactic acid as it may we can use, by using this polylactic acid we can prepare screws, pins and anchors. Okay, it is used in a number of biochemical applications like drug delivery and dialysis media, and it is used in the preparation of plastics packing and food plastic packing for foods and disposable tableware, and it is also used for making compostable packing materials and food packing, etc. And second example for biodegradable polymer is polyvinyl acetate. How we can prepare polyvinyl acetate? See, the polyvinyl acetate is a monomer. It will undergo free radical vinyl polymerization. It will form polyvinyl acetate. In this, the monomer is vinyl acetate. See, the properties of the polyvinyl acetate is it having the glass transmission temperature between 30 to 45 degrees centigrade, and it is resistant to oil and grease as well as solvent. It has high tensile strength and flexibility. The polyvinyl acetate has high tensile strength and flexibility. The degree of polymerization of these polyvinyl acetate is 100 to 5000, and it can be treated with alkali. In presence of alkali, this polyvinyl acetate will undergo degradation, forms this alkali acetate and the polyvinyl alcohol. The polyvinyl alcohol also can be prepared by using the polyvinyl acetate. The polyvinyl acetate treated with alkali, it will form polyvinyl alcohol. Okay, by using we can prepare polyvinyl alcohol from the polyvinyl acetate in presence of base. Okay, it decomposes rapidly above 200 degrees centigrade. Above 200 degrees centigrade, it will undergo decomposition. Polyvinyl acetate undergo decomposition. It undergoes pyrolysis at high temperature. At high temperature, it will undergo pyrolysis. The polyvinyl acetate does not cross-link and it can be dissolved in many solvents other than water. Okay, the polyvinyl acetate does not form any cross linkage with any solvent. Okay, so it will soluble in all solvent except water. The applications of the polyvinyl acetate are the emulsified polyvinyl acetate. If you add any emulsifier to the polyvinyl acetate, it can act as a water-based adhesives like paste and glues. Okay, it is used in eye drops and hard contact lens solution as a lubricant. It is used in a eye drops and hard contact lens solution as a lubricant. It is used as a protective chemical resistant glue. It is used as a protective chemical resistant glue. It is also used in 3D printing as a support structure. It is also used in a 3D printing as a support structure. It is used as thickness modifier in a polyvinyl acetate glues. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.